Welcome everyone. For today's prep, we're going to keep looking at derivatives of exponential and log functions, but this time we're going to see how it works in conjunction with the chain rule. And we're going to call these kind of special versions the general exponential rule and the general log rule. So, if we remember, the chain rule helps us differentiate when we have a composite function. So, our first kind of version of the chain rule we're going to look at is for exponentials. And it's going to be things like this: e raised to some function g of x. And in this case, the exponential function is our outer function. So if you remember back when we talked about chain rule, there was the outer function for our composition, and then there was the inner function, the terms that are being plugged into that outer function. And so our inner function in this case is the stuff that's up in the exponent, and our outer function is that exponential. All right, so how do we differentiate something like this? Well, if we remember, the chain rule said when we go to differentiate, we start by differentiating that outer function. So we got to kind of break through the different layers of our function here. So we differentiate the outer function. We keep our inner function exactly the same. And then we multiply by the derivative of that inner function. So this was our chain rule. Differentiate the outer function, keep the inner function, the terms that are being plugged into that exactly the same, and then you get to the stuff that's inside and you can differentiate. So for our case here, we're going to start by differentiating our natural exponential function, and this one we know works really nice. The derivative of our natural exponential function stays exactly the same. So then we keep the same inner function. We don't make any change. And then we multiply by the derivative of our inner function. So for our purposes, what happens, the way this general exponential rule works, is our exponential term stays exactly the same. Actually, let's make that green. That's the derivative of our outer function. So that's going to stay exactly the same. You don't make any change. You don't make any change to the exponent. You don't make any change to the e. And then we multiply by the derivative of the stuff that's up in the exponent. So we're just going to multiply by the derivative of all that stuff that's up there. All right, so let's try an example just to kind of see. This is all theoretical. Let's see how this actually looks with a few examples. So we're going to use this general exponential rule, and let's start with e raised to the power 5x. So we want to calculate the derivative of this. And when we look at this, we've got an exponential term, but up in the exponent, it's not just x. There's other stuff. So whenever we see other stuff up in the exponent, we have to use this special rule. All right, so let's try it out. We're going to calculate the derivative of this. So we'll call our derivative y prime. And how does it work? Well, this exponential piece stays exactly the same. Make no change. So we'll end up with e to the 5x. Then we take all that stuff that's up in the exponent there, and we're going to multiply by its derivative. So we're going to take that 5x, and we're going to multiply by its derivative. And this is precisely, the exponential part stays the same, and then we're multiplying by the derivative of the stuff that's in that exponent. And if we finish, derivative of 5x is just 5. So we end up with e raised to the 5x times 5. And it's usually a good idea. Take this constant that's kind of at the end and just move it to the front. It's easy to lose track of things like that. All right, there we go. Let's try another one. So now the next function is f of x equal to e raised to the 4x squared minus 3x. And again, it's an indication that we have to use this rule because this is not just e to the x. We've got a whole bunch of stuff up there in the exponent. So when we go to differentiate, we'll call our derivative f prime. And how does it start? Well, the exponential term just stays exactly as is. We don't make any change to it. So e to the 4x squared minus 3x. So the exponential part, when we differentiate, doesn't change at all. Once we've kind of broken our way through the exponential, though, then we do have to differentiate that stuff that's inside. And we multiply by the derivative of those terms that are in the exponent. All right, so we gotta do our derivative here. What's the derivative of 4x squared? Well, that's just 8x. Derivative of negative 3x is negative 3. And because we've got a few terms here, let's write it out. We just got to remember the parentheses. Whoops, not 4. E raised to the 4x squared minus 3x times, and then we end up with 8x minus 3. And because there's some addition and subtraction going on in here, we need those parentheses. All right. So that's the general exponential rule. Again, remember those parentheses. So just like exponential functions, log functions have a similar type property or a similar type rule. And we're going to look at those next. So there's a special version of the chain rule for log functions. So let's see how this one works. And we're going to use this rule when the outer function is a log function. And then we've got some x terms that are being plugged into that outer function, that natural log. So as an example, let's just kind of see. Let's look at the first one here. We've got y equals natural log of 2x plus 3. Once we go through this rule, we're going to see how to differentiate this. But what do we have here? It's not just natural log x. We've got the natural log portion. So we've got that. That's our outer function. But then we've got a whole bunch of other stuff going on inside of that. It's not just natural log x. So if it was natural log x, just that, we know how to do that derivative. But because it's got all this extra stuff in there, we have to use this special rule. All right, so what is chain rule? Again, remember, this is all related back to our chain rule here. What does this chain rule tell us? Well, we got to differentiate the outer function. So the outer function here is natural log. And the inner function is whatever is inside, that g of x term. So when we do chain rule, we start by differentiating that outer function. So we got to get the derivative of that outer function. All right, so what do we know about natural log? If this was just plain natural log x, the derivative of natural log is 1 over x. So that's what we're seeing here. We're seeing the derivative of the natural log part, and it's giving us this reciprocal. Use blue. So this is the derivative of that natural log part, and it's the reciprocal of the inner term. So we know for plain natural log x, the derivative is 1 over x. So when we differentiate this outer natural log function, we're going to do the reciprocal, but then we keep the inner function exactly the same. So that's why we're seeing g of x in the denominator here and not just x. So derivative of the natural log part gets us this reciprocal, but then we're keeping the term inside the log function in that reciprocal exactly the same. And then, next door to that, we've got to multiply by the derivative of whatever was inside the log function. So we have our derivative of our inner term right next door that we're multiplying by. All right, so let's try this out. So we'll keep that rule in view here. So we've got this natural log of 2x plus 3 function. So we're going to differentiate that with our chain rule. So our function's called y, so we'll call our derivative y prime. And how does this start? Well, we have to first differentiate our way through that log function. We got to break our way through. And so when we differentiate that log function, we do the reciprocal of whatever was inside. So we're going to end up with 1 over, and the inner function there is 2x plus 3. And then we're going to multiply by the derivative of 2x plus 3. So again, we've got the reciprocal of the inner function times the derivative of the inner function. And if we calculate this, derivative of 2x plus 3 is just 2. So we end up with 1 over 2x plus 3 times 2. And usually a good idea, take the 2, just multiply it into the numerator. So we end up with 2 over 2x plus 3. All right, so we got our derivative there. Let's try one more. So let's try the next one. So we've got natural log. Let's see if we can, maybe we can keep the rule in view there. So we've got natural log of a whole bunch of stuff inside it. So it's not just natural log x that we're looking here. We've got the natural log, but then we've got all this other stuff inside of it. So when we calculate the derivative, call our derivative here y prime. Again, let's look at what is all the stuff that's inside. Well, it's this x cubed plus 5x squared plus 8. So when we first differentiate our way through this log function, we've got to break our way through. The first thing we do is we do the reciprocal. So we're going to take the 1, make this into 1 over x cubed plus 5x squared plus 8. So we get the reciprocal of the inner function. And then, right next door, we're going to multiply by the derivative of that inner function. So again, if we go back up to the original rule here, when we're differentiating natural log of a whole bunch of x terms, the reciprocal is the derivative of that natural log part. We keep the inner function exactly the same. We don't make any change to that. And then we differentiate the stuff that was inside. So if we finish doing that derivative, we end up with, well, our fraction we're done with, so we don't got to do anything with that. And then derivative of x cubed is 3x squared. Derivative of 5x squared is 10x. And then the derivative of that 8 is just 0, so we won't write that. And if we're going to leave it like this, we need the parentheses there. So again, be careful. A lot of these chain rule type ones, you got to have the parentheses. Now we could also do kind of what we did in the previous one and take this term and multiply it into the numerator. So how would that look here? Well, we would take the 3x squared plus 10x, and we take that whole thing and just move it into the numerator. And if we did that, we don't need the parentheses anymore. So this would become 3x squared plus 10x all over x cubed plus 5x squared plus 8. All right, so we got our derivative there. Alrighty, so we're going to be practicing some more of these special derivative rules in class, and looking at some of our old application type problems as well with them, finding and classifying critical numbers and all of that. So we'll see you then. Bye-bye.